Johnny here with Simpson Math, and in this video we will be covering verifying trigonometric identities. Now, before we even begin, let me remind you of the identities that we've talked about so far. So in previous videos, I just kind of littered the lectures with some identities. So let's go through those real quick. And we call all of the identities we've talked about thus far the fundamental identities. Fundamental. And we just now accept these as true. So I tried to explain where they came from and like what they are. But now after today, we just know them to be true. So we started off with those quotient IDs. And these came directly from the definition. We said sine was y over r, cosine was x over r, tangent was y over x. And so if we just put sine on top of cosine, we can reduce the r variable and we come up with y over x, which is just tangent. So we can call tangent of any angle sine of that angle divided by or over cosine of that angle. Similarly, cotangent of an angle would just be the reciprocal, but by definition it is just cosine over sine. Those two identities are the quotient identities. We also talked about the reciprocal IDs. These also came directly from the definitions. And they're like the first thing we learned. But if I had sine of an angle, well, that's just going to be the reciprocal of cosecant. And likewise, cosecant is the reciprocal of sine. Similarly, cosine is the reciprocal of secant, and secant is the reciprocal of cosine. Then we have tangent and its reciprocal. And if you ever see a cotangent, you can think of it as, or replace it with, something it's equivalent to, the reciprocal of tangent. So these came from the definition. They were early on in this lecture series. All right. Then let's see, we came across, the cofunction. We talked about this a couple times. One, it was the triangle. If that angle is alpha, I'll just use alpha, then the other angle in the triangle must be 90 degrees minus alpha, or pi halves minus alpha. We also talked about cofunction when we were graphing the trig functions, and that was just a sort of horizontal translation, and also like a reflection. But here they are. If you have sine of pi halves, or 90 degrees, minus theta, then you're just talking about that other angle in the triangle. And if sine of pi halves minus theta should be opposite over hypotenuse, then cosine of the other angle is that same thing, this side length over the hypotenuse. So sine of 90 minus theta is simply cosine. All right. And it works both ways. Cosine of pi halves minus theta is equal to sine. Works on the unit circle, works on triangles. The graphs are identical. If I were to graph sine of pi halves minus theta, and I were to graph cosine on the same Cartesian plane, they are identical. They are the same thing. And sine and cosine are co-functions. Cosine is the cofunction for sine. So if I have secant, well, secant has a cosecant. And we can write it this way as well. Cosecant of pi halves minus theta is secant. And then tangent has a cotangent. Tangent of pi halves minus theta is cotangent. Cotangent of pi halves minus theta similarly is equal to tangent. Cofunctions. We also have the even and odd. I'll do them kind of separately. Even. We talked about this, the graph of cosine and the graph of cosine of a negative x were the same graph on the Cartesian plane. So cosine of an angle is identical to cosine of a negative angle. That makes sense on the unit circle. It makes sense graphically. Its reciprocal secant is also even. And it just so happens that the other four trig functions happen to be odd. Normally, there's that's just not, it wasn't guaranteed to be that, but it is. All right, so we have the odd relationship. And the odd relationship is a double reflection. So this even was a reflection about the y-axis. Odd is both around the y and the x-axis, or you can think of it as a reflection about the origin. But if you take a negative sine wave, it's equal to a sine wave being reflected about the y-axis. So negative on the outside affects sine, and negative on the inside the same way. And that relationship is true for the remaining ones. So a negative cosecant of theta is equal to cosecant of a negative theta. Negative tan is equal to tan of a negative angle. And if I take the cotangent graph and reflect it about the x-axis, it will look identical to the cotangent graph being reflected about the y-axis. This works for the unit circle, it works for the graphs. Those are even and odd identities. I think there's just one more I need to write down, and that was the Pythagorean identities. These came from the Pythagorean theorem. We showed it on the unit circle for sure. And these are fun. If you have sine squared of an angle plus cosine squared of an angle, it is always equal to 1. I showed this on the unit circle. This is just the Pythagorean theorem. This basically says y squared plus x squared, and that has to equal that hypotenuse squared if you're using the Pythagorean theorem. Well, the hypotenuse on the unit circle is always 1. So any y value squared plus any x value squared will always equal 1. That's the Pythagorean theorem. We then used the Pythagorean to derive the other two. So go back in those videos if you want to check that out again. But let's see, that would be 1 plus cotangent squared equals cosecant squared. And then we have tan squared plus 1 equals secant squared. So altogether, I think there's 27. Let's see, 3 and 6, 9. Another 6 is 15. Another 6 is 21, 22, 23. There are 23 fundamental identities. I've just kind of sprinkled them in the previous lectures. And I think along the way I was saying start to make a list, make some note cards. But here I've gathered them for you. So make sure you have a nice list of these that you can quickly reference. When we verify trig identities, we're going to be using these identities over and over again. And we need something to just help us recall all of these identities. So pause the video, write these down, collect all those identities. If you have questions about where these came from, there's two ways to look at that. One, no, you can no longer question this. I'm telling you these are true, and after today we have to accept them as true because we're going to be using them from now on. But if you are curious about, okay, well, I know I really don't know where that came from, then go back and check out the previous videos. Ask me and I can kind of help you. But just play with it. Play with the graph. Play with plugging in values. So if you really don't know that this is true or not, you can plug in an angle like 45 degrees and then ask yourself, does that really equal cosine of a negative 45 degrees? Similarly here, does cosine of 45 degrees really equal 1 over secant of 45 degrees? So go play with them. Those are not necessarily proofs, but seeing those examples will help like solidify, oh yeah, this is true. And oh yeah, that will work for any angle on that unit circle, any angle. Okay. Good. We've got the fundamental identities. Now moving forward to verify trig IDs. All right. We now accept the fundamental identities, and what we're going to do is use them to verify other trigonometric identities. And we're going to do this in a very formal way. So moving forward in our math career, later in this course, and then throughout the calculus sequence and beyond, math is about proving certain things. So we're going to need to prove theorems and the like. So verifications are like a baby form of proofs. They're not proofs, they're verifications, but they are formal, just like a proof is. So we're going to learn how to write things down formally with these verifications. Okay, so we're going to be given a trigonometric identity that is true. So right here we've given one, sine beta over tangent beta equals cosine beta. And then we have to verify, we have to prove that it is true. It is, but we have to show it. All right, now the way we do it is we're going to choose one side of the equation to manipulate. Now, depending on your textbook or teacher or where you are in math, they may allow you to do like both sides of the equation, but for our purposes, we are only allowed to manipulate one side of the equation in our final formal write-up of the verification. I'll talk about manipulating the other side of the equation in a like off to the side type setting, but in our formal write-up, I cannot touch one side of the equation. All right. Then, as we move along, we're going to be changing, we're going to be manipulating like one step at a time. So I'll start with something. I will do something to manipulate and change it, do something to it and change it over and over again, and a step-by-step process. And every single time that I make a change, I must justify what I've done. Even if I just took 2 plus 2 and added it to make it 4, I need to say I added in this step. Very formal, I've got to justify my steps. All right. So for our first example, we have sine beta over tangent beta is equal to cosine of beta. We need to verify that this is true. We only have a few manipulation tools up our sleeve. But my first glance, I see tangent and I see a sine and a cosine, and I'm thinking about that very first identity that we added to our identity list of those fundamental identities. So go back and look at it. Very first one, tangent can be rewritten as sine over cosine. I think I'm going to use this one. But that's not the only time tangent popped up. Tangent could also be written as 1 over cotangent. It could be written as cotangent of 90 minus theta. It pops up a lot. But this one seems to kind of go with the flow of the identity that we're working with. So I'm going to use this identity to make a substitution. I think I'll use some color here to help show what I'm changing. That tangent beta can be rewritten as sine beta over cosine beta. I'm going to bring down the equal sign, and I'm going to bring down the right-hand side of the equation. I had the verification, I did something to it, and now it looks like this. I need to justify, or I need to explain what I just did. So what does allow me to take tangent and rewrite it as sine over cosine? What allows me to make that substitution? Well, it's a quotient identity. Now these justifications, these proofs, they are written in such a way that a peer of yours could follow along. So you are a student of pre-calculus, you are a student of trig, you should be able to hand this piece of paper to a classmate or someone taking trig, and they should be able to follow your work. So when they see this identity and they say, oh my goodness, how did they go from tangent, like how do they rewrite this? They might not know at first, but they come over here and they say, oh, they used a quotient ID. I come look at my quotient identities. Oh, there's one. Oh, tangent is this. So if a peer can follow your justifications, and you're doing so correctly. Or you could think of it as, could you follow it? You are your own peer. So if you write down a proof, you sleep, and the next day you're reading it and you ask yourself, how did I get from here to here, and you don't know, then your justification wasn't good enough. Alright, so here I've justified though. The quotient ID allows me to rewrite tangent as sine over cosine. Okay, now this is just something being divided by a fraction. We know how to divide by fractions. So several of my students do like a keep, change, flip. That's how they learn it. I like that. That's a fun, easy way to do it. So I'm going to divide by a fraction. You could think of it as multiplying by the reciprocal. You could probably multiply through by some sort of fancy one here. But I'm going to take this sine b. That's keeping the numerator as is. I'm changing the division problem to multiplication. And then I'm multiplying by the reciprocal instead of what's down there. Again, I'm bringing down the equal sign, and I'm bringing down the right-hand side of this equation. So it's one step at a time. Now, how did I get from that freaky-looking fraction to look like this? Well, I called that keep, change, flip. Now, that's not universal, but I think everyone would understand. If you're dividing by a fraction, you need to maybe multiply by the reciprocal. Everyone should understand that part. Oh, and if I multiply, then I have a sine b in the numerator position and a sine b in the denominator position. So what's going to happen to those sine b's? They're going to reduce. You could say divide. That would work. So the justification, you could say divide. But sine b divided by sine b is just going to reduce to 1, leaving me with cosine beta equaling cosine beta. The left-hand side of the equation is identical to the right-hand side of the equation. I only have one more thing to do, and that's to say I'm done. In a proof that's commonly done by drawing like a little subscript black box. That's how most textbooks do it. Back in the day, they would say QED. This is Latin. I didn't learn Latin, but I think it's quod erat demonstratum, something like that. It means like I've done what I set out to do, or I've proven what I've set out to prove. Basically, I'm done. I did it. For my students, these are your proofs, so you can come up with your own symbol that means you. So if you want to do like a Triforce, or the Deathly Hallows, or a butterfly, something that says, hey, I did this proof, I justified it, I showed step-by-step work, this is done, I did it, here it is. Alright, we verified our first trig identity. Now, the manipulation, let me talk about that. There's only certain things we can do to manipulate one side of the equation. If we had gone back to the original thing we were given, if that were an equation, then it is legal to multiply both sides of the equation by tangent beta. Maybe you would like to do that to get rid of this denominator. And that's not allowed here because I'm not allowed to touch the other side of the equation. So I'm not allowed to multiply through by like both sides of the equation. That's not allowed. What is allowed though is multiplying by 1. I can take this fraction and multiply by 1 because it doesn't change the value of it. We do that a lot when we're multiplying or when we're trying to get like a common denominator. We multiply top and bottom by that factor we need to make that common denominator. So we can multiply by the multiplicative identity 1. And I just said like 1 could be really fancy. Maybe you need cosine x over cosine x. That is a form of 1. So that is legal manipulation because it only affects one side of the equation. Similarly, you could add a number. Now back in equation days, I could add 5 to both sides of the equation. But wait a second, I can't touch the right-hand side in these identities. So is there a number you can add that doesn't change the value? That would be the additive identity. You can add 0. Well, of course that doesn't change anything. It's just adding 0. Now, that may not make much sense, but think about this. What is cosine x minus cosine x? Don't those cancel to 0? So I could add this to the left-hand side, and that's a form of 0 that I'm adding. It's pretty fancy, but it's legal. I don't know how often we'll use that one necessarily, but that's just something we can do. What we did was substitution. This is typically an identity that we know, like a fundamental identity. That's what we did in the very first step. We just substituted. Oh, and then this was just like arithmetic or algebra. That's allowed, of course. If you're given something to add together, yes, you can add them together. So like 5 plus 5 is 10. Yes, you can do this arithmetic. I needed to divide by a fraction, so I did so. I multiplied by the reciprocal. I did it. Perfect. Reducing. That's just algebra. You can slash through. You can divide. That's arithmetic. Let me talk about the word reduce. There's other words I could have used. Division. Sine divided by sine goes to 1. The word simplify is not quite good enough. Yes, everyone would understand you simplified these b's and they went away, the sine b's. But simplification can also mean like adding like terms. It can mean like something canceling to 0. So simplify is a little bit too vague when we're talking about a formal proof. I mean, yeah, it's just a little too vague. So try to avoid the word simplify. What type of simplification did you use? Here I reduced or I divided. This, the cosine minus cosine, you could say add or subtract. This is canceling. So if you said the word cancel up here, that's also not quite right. Everyone says it. Everyone understands, yes, these sine betas are canceling. But actually, no. Cancel means they go to 0. So this cosine x minus cosine x, this is cancel. These are reduce. So you reduce to 1, you cancel to 0. If that is confusing, then maybe you should use divide and subtract. That may be better. Okay, we have verified our first trig ID. Let's go on to another identity. Started with that. Changed it, justified. Just manipulated it, what I'm doing. Did stuff, what did I do? They're identical, black box and dead. In our next example, we need to verify that cotangent alpha times cosecant alpha times secant alpha is equal to cosecant squared alpha. Okay, good. All right, now these verifications, they're a lot like a jigsaw puzzle where we have the answer. So like on a jigsaw puzzle, you know what the picture is supposed to look like. So you know where you're supposed to go. And then you have all the puzzle pieces. That's your algebra skills, those fundamental identities, and you're just trying to put the pieces together in order to get there. I think you may agree with me that I cannot teach you how to work every jigsaw puzzle that's out there. It's going to be true for these identities as well. I can't show you every single one. I can't, do that. But what I can do is teach you different techniques. So different strategies when working these identities. So just like in a jigsaw puzzle, it's probably smart to start with the edge of the jigsaw puzzle. Those pieces are nice and flat, so you can kind of put them together. And then you can work on, this polka dot pattern comes up a lot. Let me put all those pieces together. Or this is a red barn, so I want to get all the red pieces together and kind of work on that. So there's different strategies for working in a jigsaw puzzle. There's some different strategies when dealing with these identities. The first strategy or technique that I'm going to talk about is rewriting in terms of sine and cosine. So back at the beginning of the semester, I defined sine was the y value over the radius and cosine as the x value over the radius. And everything we have talked about since that day is based off those two definitions. Everything is based off sine and cosine. So one strategy is when you see these reciprocal functions and the quotients, rewrite them in terms of the building blocks of trig, sine, and cosine. So that's what I'm going to do. When I see cotangent, I don't see a cotangent function. That's not what I see. I see a cosine in the numerator position and a sine in the denominator position. Go back to the ID list. Cotangent can be rewritten as cosine over sine, the building blocks. I'll use color to help me get my point across. Cotangent is cosine alpha over sine alpha. Cosecant, well, that's a 1 and a sine. This is 1 over sine alpha. Secant, I see a cosine in the denominator position. So I'm going to substitute 1 over cosine alpha. Bring down the equal sign, bring down the right-hand side of the equation. Now, what allows me to do that? What allows me to make all these substitutions? And yes, I did more than one thing in one step, which is okay, especially if I'm doing it like this. I don't want to make this switch and then another switch to this pink stuff. I feel like this is okay because I'm saying in this step I'm going to manipulate that and that and that. I think that's okay. Don't get too carried away. But here I used a quotient identity, and then here I used 2 reciprocal IDs. Again, these justifications, a peer must follow, or think of it as you sleep for a week or you come back to this a year later. Can you still follow your work with your justifications? So QID, hopefully that kind of clues in. There's an identity, and there's some quotient. These are reciprocals. Oh, and I've used 2 of them. So maybe like a times 2. Some things say I've used a quotient identity and I've used 2 reciprocal IDs. Now everything has been rewritten in terms of sine and cosine. And I see now how they can be put together. You all see the cosine up top and the cosine down below? What's going to happen to those cosine alphas? They're going to reduce. cosine over cosine, if I were to multiply those, cosine times 1 over cosine, those reduce to 1. You could also call this a division. You could say cosine and its reciprocal. When you multiply something by its reciprocal, it always goes to 1. You could say that. Multiplying cosine by its reciprocal goes to 1. But I'm going to make the switch now. This is 1 over sine alpha times 1 over sine alpha equals, bring down the equal sign, bring down the right-hand side of the equation. Now there's a couple ways I could do this. I think one, I'll just explain visually what's going on, and then I'll show a different way. So I think everyone agrees 1 over sine is just cosecant. 1 over sine is just cosecant. Cosecant times cosecant is cosecant squared. Okay. Instead of doing a reciprocal now, I think I'm going to multiply first. So if you have 1 over sine times 1 over sine, you have 1 over sine squared. Now I wanted to show this because I have a lot of students that get confused by this next step. If you have 1 over sine squared, that is simply cosecant squared. It's the reciprocal. Yes, there's a 2 on there, but we just kind of explained what's going on. If you have 1 over sine squared, you've got this going on. So you have a reciprocal and another reciprocal. So you've got that reciprocal, that squared, cosecant squared. So I'm taking the 1 over sine, and if we put a little 2 there, it's still going to be equal to a cosecant squared. I'm going to make that step, or that substitution. This is cosecant squared alpha. What's allowing me to do that is a reciprocal ID. My left-hand side is identical to the right-hand side. I can black box this and be done. All right. For this verification, I'm trying to multiply sine minus cosine and sine plus cosine, and I need to verify that it is equal to 1 minus 2 cosine squared. Okay, my technique here is just do it. I claim when any math student looks at this equation, pretend you're not even in trig. If you just look at this equation, one side of the equation is just saying, do me. Like, there's something you can do to my side of the equation. Do me. And I claim it's the left-hand side. You have a binomial being multiplied by a binomial. We've done this so much in math that it's just screaming like FOIL. So I'm going to distribute what I have on the left. So this is my just do it technique. If you see two fractions being subtracted, just do it. Get the common denominator and subtract them. If you see binomials like this being multiplied together, well, just do it. Just go through the process of that math. Okay, so you may want to call it FOIL. I'm doing just distribution. So I have sine times sine is sine squared. Sine times cosine is just that, sine cosine. Then I have a minus sine cosine. And then I'll have a minus cosine squared x. Now I've kind of run out of room over here, but this is a common thing I will do. I'm not supposed to touch the right-hand side of the equation. So one thing I do is I just replace it with RHS for right-hand side. RHS for right-hand side. That's just so I don't have to recopy the right-hand side every single time, especially if this gets longer and longer. That just saves me some time and ink, and I'm not supposed to be touching it anyways. Now, of course, I am trying to get there, so I do want to know, like, look at it and know what I'm going toward. All right. Oh yeah, the middle two terms, those are going to cancel to 0. They're going to add together, add like terms, and they're going to cancel each other out to 0. Now this is happening because the two binomials that we were given are conjugates. I think I'm going to come back and talk about that word conjugate, because that's going to happen a lot with these verifications. But I see, oops, before I even continue, I need to move on. I need to justify. What allows me to take those things and rewrite it as these four things? Well, I multiply it. You could say distribute, means same thing, that's probably more accurate. You could say FOIL, that's fine. Anyone would know what that means. But I just multiplied here. And in my next step, I'm going to cancel. You could say add like terms. You could say add. You could say subtract. All of those make sense. Basically, these cancel each other out, leaving me with sine squared x minus cosine squared x equaling, I have the room this time, so I'm going to go ahead and copy down 1 minus 2 cosine squared x. Okay, interesting. So I've just done it, but now I have like a new problem to worry about. How in the world does this difference equal that difference? And I'm looking at them, and the one on the left has a sign, and the one on the right does not. So I kind of need the sine squared to go away. There's a couple ways to do that. Maybe I could substitute something that it is equal to. So I'm going to look at my fundamental list, and I'm really looking for a sine squared, and that does sound familiar. All of these are linear in nature, but when I get down to the Pythagorean, notice I have a sine squared theta. Oh, I really wish it was sine squared theta all by itself. Well, I can do that. This is a true statement. We said we have to accept this as true. Well, if this is a true equation, then I can manipulate it. Now, this is not part of my verification process, as in this equation, I can manipulate the left and the right-hand side of the equation. So if I wanted to multiply everything by 5, that's legal. I, though, just want to get it by itself. So I'm going to subtract both sides by cosine squared. Let me show you what I mean. I'm going kind of like off to the side. So if you wanted to do this in the formal proof, just be very careful. This is my proof, so I don't want to throw in math that doesn't make any sense. So let me maybe come down here and go like off to the side. OTS. Off to the side. I'm going to write down the Pythagorean identity that says sine squared of any angle plus cosine squared of that same angle is equal to 1. Well, I can solve for sine squared. That is, I can go through and I can subtract both sides of the equation by cosine squared alpha. Well, that's going to leave me with sine squared alpha, cancel, equals 1 minus cosine squared alpha. So I've just taken the Pythagorean identity and I've varied it a little bit. I've made a manipulation to it. But it's true. Sine squared theta is equal to 1 minus cosine squared theta. I'm going to use that as my substitution. This sine squared, I'm going to replace it with 1 minus cosine squared x. I'm going to bring down my minus cosine squared x. I'm going to bring down my equal sign. I'm going to bring down the right-hand side of the equation. Now I need to justify this in some way. So what allowed me to do this? It wasn't just the Pythagorean identity. I took the Pythagorean identity and I manipulated it just a little bit. I'm going to call that a Pythagorean variation. I think if I gave this to a peer of mine and they said, how in the world did they get from this step to this step? They used color, so that was helpful. And they said the sine squared of x is going to become this. And they used the Pythagorean variation. Oh, well, I would go off and I'd say, well, Pythagorean means something to me. There's one with a sine squared. And if I just vary it just a little bit, then yeah, I could come up with this. So I think I've done enough justification to get me to the next step. Now look at that. I have like terms, so I can simply add these together. You're not done until they are identical, left and right hand side. A negative something minus another negative of the same thing, you've got -2 of those now. All right. I think I'm done with that one. So I said those two things were conjugates. And I think now's a good time just to remind you of what a conjugate pair is, because they are very helpful and they show up a lot with these verifications. So this is not part of, like, I'm not verifying, I'm just going to talk about conjugates just because I want to. Let's see. All right. Nothing to do with verifying trig IDs other than these come up a lot. Conjugates. When I say conjugate, do you know what I mean? If I said, I've got this binomial x plus d, what is the conjugate? It has a conjugate pair. What is it? Same two terms, same x and same d, but you're subtracting instead of adding. So the conjugate pair for x plus d is x minus d. And this is cool because of what happens when you multiply them together. We just did something very similar with sine and cosine, but now I'm using x and d just for practice. This is x squared. I have a minus dx and a plus dx and then a minus d squared. What cool thing happens? Oh, the two middle terms add to 0. And I get x squared minus d squared. Conjugates always do this. Let's play around some more. Let's take some trig, like cosine theta plus 1 and cosine theta minus 1. Cosine theta plus 1 has a conjugate. Same thing, cosine and 1, but instead of adding or subtracting. And when we multiply, I think those two middle terms are going to cancel each other out, but let's play with that. Cosine times cosine is cosine squared. You have a -1 cosine and a +1 cosine. And 1 times -1 is -1. Yep, these two middle terms cancel each other out, leaving me with cosine squared theta minus 1. Now this is very helpful with the trig because notice I went from this linear stuff to now it's this like quadratic stuff, this power of 2, which allows me to apply a Pythagorean identity. In fact, that looks a lot like Pythagorean because there's a 1 in there. So it's going to come up a lot. While I have you on the subject of conjugates and I'm teaching math, let's talk about this one. I have a binomial, 2 minus the square root of 3. What is the conjugate? Well, it's the same 2, it's the same square root of 3, but instead of subtracting, I'm going to be adding them. When you FOIL that out, we should get 4 terms. The middle 2 should cancel each other out. That's happening because they have opposite signs. Let's go through the process. 2 times 2 is 4. 2 times root 3 is 2 root 3. Then I have a negative 2 root 3. And then negative root 3 times root 3. Oh, that's fun. That's going to be a minus, and this is root 3 being squared. So what's going to happen there? Well, root 3 times root 3, I guess technically is the square root of 9, and the square root of 9 is 3. So this square root and the square, they kind of just undo each other, leaving me with that radicand, what's under the radical symbol, the 3. Oh, now this is extremely powerful. Notice I went from irrational numbers to now just an integer. This is how we simplify or like rationalize denominators. With our unit circle, we had a lot of just simple radicals down below, but if you where you can just multiply top and bottom by root 3. But if you have a binomial like this, and you're trying to rationalize, get rid of the radical. Well, you can get rid of the radical by multiplying by the conjugate. It's gone. Cool. Let's do one more thing. It pops up in math. We call this a complex number. It's got an imaginary part. I have 3 minus the imaginary number I. This thing doesn't even exist. 3 minus I. Doesn't exist, but I want to multiply by its conjugate. What is the conjugate of 3 minus I? Well, it's the same thing, but a plus. I kind of know now that the middle two terms are going to cancel out, but let's do it again. 3 times 3 is 9. Plus 3i minus 3i minus I squared. Oh yes, the middle two terms cancel each other out, and I'm left with this interesting thing, negative I squared. Well, I is the imaginary number, and it has a definition, or it is defined as the square root of negative 1. So I is the imaginary number. It comes from the square root of trying to take a negative 1. I'm going to make that substitution. I is the square root of negative 1. So I have 9 minus that I, which is the square root of negative 1, being squared. Oh, well, what happens to the radical and the square? Don't they just kind of cancel each other out? Or the square root of negative 1 times the square root of negative 1 is the square root of 1, which is somehow just 1. Okay, so 9 minus, or actually the square root of 1, there's a positive and negative result. Oh, that's kind of confusing. But anyways, I'm left with negative 1, and that's because the square root and the square are kind of like undoing each other. Oh, I got this. 9 minus negative 1, that turns into an addition problem, and you're adding and you get 10. Oh my goodness. Okay. Oh my goodness. This went from something that's imaginary, but when you multiply by another imaginary thing, I got a real number. I know the number 10. That's tangible. I know what 10 looks like. So something imaginary times its conjugate is something real. That's extremely powerful. So these conjugates are extremely powerful. And right now we're in trig world, dealing with conjugates, or heck, even this, we're doing this too. We have a lot of irrational numbers when it comes to simplifying those exact values on the unit circle. We're dealing with irrational numbers, and right now we're dealing with treating trig things as expressions. And the conjugates are extremely powerful. They are a way to manipulate what we're dealing with. Now, I said before, we can't just willy-nilly multiply by random numbers. The only thing I'm allowed to multiply by is 1. But I think maybe you can agree. Cosine theta plus 1 over cosine theta plus 1. That's a very fancy way of saying 1. And yet, that would be the conjugate to cosine theta minus 1. Okay, so I just wanted to go off on that little conjugate tangent. I think some of this information may come in handy in a little bit. All right, let's move on to another technique, though. For this identity, I'm going to talk about a technique where we start with the busy side. So I'd like to verify that cosecant to the 4th is equal to cotangent to the 4th plus 2 cotangent squared plus 1. All of those being an angle of x. All right, and there's a left-hand side and there's a right-hand side, and there's more going on the right-hand side. So typically it's easier to clean up a mess of algebra than to make a mess. Like how to add stuff to the left-hand side is not as easy as maybe cleaning up the right-hand side. All right. Now, another strategy would be when I'm working with the right-hand side over here. Well, first, just what do you think maybe we can do to that right-hand side? We could try some quotients, putting everything in terms of sine and cosine. That may work. I'm kind of looking at that, and it looks very familiar to me, thinking back to just algebra days, before I was even in trig. If I have a trinomial, something to the fourth power, plus 2 of those squared, plus 1 more. In fact, let me rewrite this in another way. If you have cotangent of x being to the fourth power, that's a lot like saying you've got something to the fourth. That's just something being raised to the fourth power. And then you have 2 of those being squared plus 1. So here's another strategy. If you're ever getting confused with all these trig functions, you can kind of replace them with a variable. Like cotangent, I'm just saying, is some sort of z. So I have z to the fourth plus 2z squared plus 1. Now notice I'm doing this on side paper. I'm not treating this as part of my formal proofwriting. I'm just playing around with what this may look like. In this form, does your old algebra skills scream at you? Trinomial? The power here is 2. This one's doubled. That makes some sense. This is old school factoring. How would you factor a trinomial? Trinomials factor into the product of 2 binomials, where the first 2 terms, when multiplied, have to give me the first term, z to the fourth. How about z squared and z squared? The last 2 terms have to multiply to give me this last term, the constant here. Well, integer-wise, I'm thinking 1 and 1. This tells us that signs are going to be the same, and that in this case, they're both going to be positive. Let's see if that makes some sense. If I were to FOIL this out or distribute, do I really get back to that? So z squared times z squared is z to the fourth power, plus a z squared, plus a z squared. I've got 2 of those, and then plus 1, yes. So we factored this trinomial. I'm going to go back to my cotangents and see if I can factor my cotangents now that I've played around with some algebra. It's a trinomial. If it factors, it will factor into the product of 2 binomials. The first 2 terms have to multiply together to give me cotangent to the fourth. I think I'm going to try cotangent squared. The last 2 terms have to multiply to give me 1. The 1 will work. Signs are the same. They're both going to be positive. That step, my justification, is I factored. I factored. There's something going on outside. Then in my next step, I'm going to, I see a square and I see a 1. So that reminds me of something on our fundamental identity list. Squares and 1s, they go together very nicely. It's written differently, but it's the same thing. 1 plus cotangent squared is the same thing as cotangent squared plus 1. When you add them together, you get cosecant squared. So I can make that substitution. These added together are cosecant squared. I'm applying the Pythagorean identity that says cotangent squared plus 1, oops, I can't talk and write at the same time, is cosecant squared. So I need to say here a justification, which is a Pythagorean identity, just straight up Pythag. I didn't have to make any sort of variation to it. I just said that is a Pythagorean identity. All right. Oh, and multiply and you get to the fourth, yes. Cosecant squared times cosecant squared is cosecant to the fourth. QED, I'm done. Here I just multiplied. When you multiply, you just add the exponents. 2 plus 2 is 4. Good. All right, I want to work this problem again using the other side of the equation, just to show you that it can be done. These techniques are not a fail-safe. I think it's easier to deal with the busier side, but that does require you to be able to factor it. So if you didn't see the factoring, or that didn't make any sense to you, then maybe you're not able to manipulate the right-hand side. So let's do this problem again. And this time I'll manipulate the left-hand side of the equation. So I'm working the problem again. For those of you who were completely lost on the factoring, or you didn't see the factoring, then this may be for you. Here's that same identity. I want to verify it. This time I'm going to choose to manipulate the left-hand side. Now there's not much going on here. I just have a cosecant times itself 4 times. Well, there is a common strategy, and I'm looking at it right here, so I'm just basically going to go in reverse, but pretending like I don't even know that's there. There is a common practice dealing with these, what we call higher order trig functions, and that is to rewrite them in squares. So you'll do this, like my Calculus 2 students are doing this right now, where they're integrating and they take these higher orders and they rewrite them in squares. So I'm going to say cosecant to the 4th power is the same thing as cosecant squared times cosecant squared. I think I'll write down what I mean. I'm going to say rewrite as squares. Hopefully that makes some sense. That's a common practice moving forward in this course. So this is another strategy I should add above me, where you take a higher order trig function and you break it apart until you can see some squares. So if I had a 5th power, I could write that as a square times a 1. So like a sine to the 5th could be sine squared times sine sine. Just taking those higher orders and busting them up into squares, because squares work so nicely with our identities. There's no 5th powers on this list, but there is a square power. There's a cosecant squared right there. You can rewrite that in terms of 1 plus cotangent squared. I'm going to do that twice. Cosecant squared can be rewritten as 1 plus cotangent squared. And I have over here still untouched the right-hand side of the equation, which is still seen right there. That's where I'm trying to get to. Now, what I'd like to do is, well, I think I'll just distribute. 1 times 1 is 1. I have one of these cotangent squares. I have another one of these cotangent squares. And now I have a cotangent to the 4th power. Oh my goodness, I almost forgot my justification here. Here I did a Pythag twice. Here I multiplied, or you could say distribute. You could say FOIL if you want to. And then I'm looking at it, but it is not quite identical. I'm just going to say rewrite. I guess technically, if I wanted to be real formal, I could say addition is commutative. 2 plus 3 is the same thing as 3 plus 2. But I'm just going to say rewrite. And I need to add these as well. So I have cotangent to the 4th, plus I have 2 of these, plus my little 1, and that's equal to the right-hand side of the equation. And on the final step, if you did use something like RHS, don't do that in your last step. Make sure the left-hand side is completely identical to the right-hand side. I know it. I know you're like, hey, why am I having to recopy this over and over again? That's just, you just gotta do it. Just do it. All right. I have done that problem now, both sides. So I claim working with the busier side is going to be easier, and that should work for you. But in this case, maybe not. Maybe that factoring was too hard to see. So working with the left-hand side, there's another way to handle it. Break it up into squares and then apply the pi factor. In this problem, we're going to try out a fancy one technique. So this particular identity, I think it would be really easy if I did the rewrite everything in terms of sine and cosine and manipulated the right-hand side. But to force us to learn this fancy one, I want to manipulate the left-hand side of the equation. Okay, so I have this identity, cosine squared of an angle is equal to sine times cotangent times cosine. I'm forced to, for whatever reason, manipulate only the left-hand side of the equation, cosine squared. That's all I got. That's a cosine times a cosine. And I need to somehow make that equal to a sine cotangent cosine. So I can go off to the right-hand side and think about what that is. And maybe I can, grab some scratch paper if I need to play around with it, kind of manipulate it. That's legal to do off to the side. So this would be sine cosine over sine cosine, using like a quotient identity. So here's another technique that I'm not, maybe right above me, is you can use the right-hand side to manipulate and play with and break it down. Like, hey, this is, that would reduce, giving me cosine squared theta. Oh, what I've done is, but I need to somehow make this equal. For whatever reason, I need to do it on the left-hand side. So you can use the right-hand side and then work your way backwards. That's a good strategy. But I see that I need some sines involved. In order to get this cosine squared to look like that, I have got to introduce sine. Okay. So it's an equation. I'm not allowed to multiply both sides of the equation by sine. That is illegal. What I can do is multiply by 1. I'm going to multiply by a fancy 1. I'm going to multiply by sine over sine. Do you agree sine divided by sine is just going to be 1? I'm introducing what I need. I need some sines in my identity, so sorry. So I'm going to throw in a sine over sine. Maybe I can cut that out. Okay. Then I am just going to kind of like rearrange it. These are all factors. I have a sine in the numerator position, a sine in the denominator position, and 2 cosines. I've got 4 different factors flying around. I'm going to just rearrange them. Multiplication is commutative. So I can, did I say that right earlier? Or addition? Anyways, multiplication can be rewritten like that. Like 3 times 2 is the same thing as 2 times 3. So I'm going to pull the sine that's in the numerator. I'm going to write that out front. Then I have a 1 over sine. Then I have a cosine in the numerator position and a cosine in the numerator position. Y'all see those 4 different factors? Okay, well, that's just cotangent using a quotient ID. All right. So that's kind of a trivial form, but that's an example where we can multiply by 1 to introduce stuff. So if your other side of the equation has a sine plus cosine, but you don't on the other side, well, you can throw in a sine plus cosine as long as you do it top and bottom, as long as you're multiplying by a form of 1. If you need a cotangent squared, well, you can multiply top and bottom by cotangent squared. All right. Let's see. I think I'm done with techniques for now, so I think I'm ending the video. I think. All right. This video, or portion of the video, I haven't decided yet, is focused on creating your own identity. So when I first introduce verifications and the process of how to verify them, I have my students create their own identity, and I typically, collect one from Sarah and give it to John and say, hey, verify each other's identities. So let's walk through the steps of what I mean by creating your own identity. So first, you just start with a true equality that everyone agrees with. You can make it as complex or as simple as you want. So my first step, let's do something like sine of x equals sine of x. This is true. No one can refute this. So basically, we're doing a verification process in reverse. So you start with something that's true. And again, you can make this, like put plus signs in there, the fractions, you can make it really nasty at the start. But I'm just going to start with sine equals sine. Step 1 is complete. All right. Then I'm only going to choose to manipulate one side of the equation. So I can't do things like multiply through by 5. If I wanted 5 sine equals 5 sine, I need to start with that from the get-go. I cannot now manipulate the other side of the equation. So if you wanted to do that, or if you do that, that's you're still working on step 1. Okay, so make your step 1. Then choose one side of the equation to manipulate. And then I want to see at least 5 steps to this problem. So that's multiplying by 1, that's adding 0, that is using identities to substitute, that type of thing. 5 of those good steps. All right, so all I have is sine. There's not much to do there. So I think I need to introduce some more stuff. So I'm going to multiply through by 1. I think if I had another sine up there, I'd have a sine square, and then I could do some Pythag. That sounds fun to me. So I'm going to multiply by 1 in the form of sine over sine. So I have sine over sine times sine. Bring down the equals, bring down the other side of the equation. And then I can multiply here. So here I'm just doing some arithmetic, but I guess this counts as a step. I'm actually doing some multiplication. Sine times sine will be sine squared. All right, pretty straightforward. Now that I have a square, I know I could use some Pythag stuff. I know, now that's going to be a variation, I think. I'm going to use some scratch paper to help me out here. I know sine squared x plus cosine squared x equals 1. That's what I have memorized. That's the Pythagorean identity. If I want to talk about what sine squared is equal to, I need to subtract cosine squared from both sides. Okay. So I'm going to use a Pythagorean variation to rewrite sine squared as 1 minus cosine squared of x. All right, so that's 3 steps. I need at least 2 more. So I have 1 minus cosine squared over sine equals sine. And let's see, what else can I do here? Oh, well, this is something kind of cool. 1 minus cosine squared of x, we call that a difference of two squares, which means we can factor that. I'm going to factor the numerator using the difference of two squares. That'll be 1 minus cosine x and 1 plus cosine x. We talked about, maybe not the difference of squares, but we talked about that reverse process. These are conjugates. When you multiply them together, the two middle terms cancel, and you're left with 1 minus cosine squared of x. So that conjugate process in reverse, that's just factoring, and that's called the difference of two squares. All right. Then, I don't know, let's see, we've done multiplication, we've done multiply by 1, we did an identity, we did some factoring. We could throw in like an even and odd identity. Cosine is even, so I can make one of these angles negative and it doesn't affect it. So I'm going to do that. I'm going to apply an even identity. So I'm going to take this one and say cosine of x is equal to cosine of a negative x. Let's see, let's do one more thing. I don't think I've shown the adding zero thing yet. What would be a cool zero to add that would make some sense here? Just add some random stuff like tangent. Yeah, I'll do that. Okay, I'm going to add 0. Now this is interesting because I'm going to choose a 0, tangent minus tangent. Tan minus tangent is 0. So if I add tan plus negative tan, then I'm adding a form of 0. So here we go. Kind of running out of room. It's getting kind of ugly pretty quickly. Oh, that's a plus sign. Oh dear, my justification kind of got in the way. But all I did to the left-hand side of the equation was I added this tangent minus tangent. That's just 0. So I didn't affect the value of the left-hand side. I just changed what it looked like. And then to make it not so obvious that those will go away, I'll just turn the first tangent into like sine over cosine using a quotient ID. And then I'll have clearly done enough 5 steps for sure. That's an x sine of x over cosine of x using a quotient identity. I still have minus tangent. I still have plus, and I still have this fraction stuff. Okay, what I have done here is I have created an identity. This is how I make problems for an exam, or how I make the homework problems. I just start with some true statement and do some manipulation, make it nice and scary looking, and then I just pick that up and I say, here you go, verify that. And I believe that's going to be one of your assignments. So go through this process. Did I do? Yeah, go through this process. And then what you're going to do is you're not going to show, or you're going to show this work to me, but if you just give this identity to a classmate, then you're just going to copy this last thing. So you'll do something like this. Verify that sine of an angle over cosine of that angle
minus tangent. I think I have a mistake here. I changed tangent to sine over cosine, and then I changed that minus sign to a plus. That's a mistake. That's a minus sign. So here I did it correctly, yes. Sine over cosine minus tangent plus that big fraction bar, which was 1 minus cosine x times 1 plus cosine of a negative x all over sine of x is simply sine of x. So this is what you would give to your classmate. You say, hey, verify this thing, and then watch them suffer. Okay. Now, I think part of your assignment is also to verify it and then turn that into me, so do that as well. But if I'm giving it to one of your classmates or you're giving it to one of your classmates, you're just going to show them this. You're going to show that last step, and you're going to tell them to verify it. And so then I'm going to see if I can verify this thing. And for sure, if you're doing your own, you could just work backwards. I could just take these same steps and go backwards. But I'm going to try to treat this like something I've never seen before. So if I first look at this thing, my eye is drawn to that. And then this is pretty obvious to me. So my eye is drawn to that. So in my first step, I'm going to do two things. I'm going to apply a quotient ID to turn this into tangent. And I'm going to apply an even ID to call that just a regular cosine. And then those are my justifications. So I'm going to show my work. This is just tangent now. This is just tangent still. I'm adding a fraction. But I'm changing that. Cosine of a negative x is the same thing as cosine of x. Okay, these clearly are going to cancel or subtract or add like terms. I think over here I will distribute, FOIL, multiply. Those are completely gone. These are conjugates. I know the middle two terms will cancel each other out. This is going to be 1 plus cosine x minus cosine x minus cosine squared x all over sine. These cancel or add like terms. Okay, well this is, yeah, I see the square and I see the 1. This has to do with Pythag. It's not quite what Pythag says though. So I'm going to go off to the side and remind myself sine squared theta plus cosine squared theta equals 1. So if I want 1 minus cosine, then that's going to be sine squared. Let's see. Sine squared theta equals 1. If I subtract that over, there we go. So again, just emphasizing, this is not part of my formal like proof writing. This is just off to the side, just kind of like some scratch work. But I claim I can take 1 minus cosine and replace it with sine squared. And what allows me to do that is some sort of Pythagorean variation. Simply reduce one of those signs, and I have sine equals sine. QED, I'm done. I've verified it. Alright, so create your own identity. It's basically just solving one in reverse. Start with something new, choose one side, start with something true, start with one side of the equation, manipulate, 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 justify along the way, make sure you're not making any mistakes, because then someone's going to work this problem. So you want to make sure it really is true. And then, yeah, that's how you do it. And let's hit the bell.